In 1859, Charles Darwin published the book Origin of Species and has sent the world into confusion ever since. This spawned the great debate between religious leaders with their big hats and naturalists with their big beards. Why? Because Charles Darwin did not complete the theory. And while the majority of the population sees Freud as a bad joke, old Chucky D here has been elevated to the status of a god, even though this guy really screwed up. So, how did the species of the world really evolve? This diagram shows a generic population distribution curve for any given species. This one will represent the size. It is created by setting boundaries for the size, such as 90 to 100 centimeters tall, and counting all of the animals that fit that criteria. In this diagram, each blue box represents one animal. Some of the animals are below average size, while others are above average. Most, by definition, are of an average size. According to Darwin, natural selection drives the evolution of species. The above-average animals will breed, causing the average size of the animals to increase. But this is not the pattern seen in nature. Dinosaurs were larger than the largest mammals, and early dinosaurs were larger than the later ones. The process of natural selection suggests that the animal size will increase when, in reality, they become smaller. If only Chucky D had identified the process of natural deselection, things would have been so much clearer. Color has a major effect on the survival of species living under the sun. There will be a natural variation in the color of each animal. Animals that are not properly camouflaged will more likely die through predation, which reduces the diversity in the color of the population. The process of natural selection reduces diversity in the population. If the animal then moves underground, color no longer has an effect on its survival. The parents will not care what color they are before they mate. Therefore, the diversity in the color increases until the color washes out and the animals become white. This is the process of natural deselection. The process of natural deselection increases diversity in the population until the attribute is lost. Attributes that are being refined through the process of natural selection will be called drivers. Attributes that are being lost through the process of natural deselection will be called sliders. Theoretically, it is possible to have a monosex species where each animal has both sperm and eggs. In a monosex community, every member breeds. This eliminates the process of natural selection, causing every attribute to slide. This leads to extinction. In a male-female community, the males fight for the right to breed. For the females, however, barroom rules apply. Every female with a pulse will find a mate. Natural selection cannot be applied to a species where all the females breed because every attribute will slide, leading to extinction. To prevent extinction, natural selection must be applied to females by removing their pulses. This fundamental problem defines the need for the predator-prey relationship. To give the predators an advantage in targeting the females, females are smaller than their male counterparts, and female predators are smaller to make it more difficult for them to kill their prey. Presented here are generic population distribution curves for a predator and prey species with neither having an advantage. Both species exist in a stable balance. If the prey gains an advantage, their increased survival rate allows natural deselection to generate sliders. This weakens the species. When it is harder for the predators, only the fittest of their number survive, causing natural selection to strengthen their form. Both species return to the balance. If the predators gain an advantage, their increased survival rate allows natural deselection to generate sliders and weaken their form. Only the fittest of the prey survive, causing natural selection to strengthen their species. Once again, both species return to the stable balance. If the predators manage to kill off all of the prey, they die of starvation. If the predators die out, the prey's attributes begin to slide, leading to extinction. Elephants clearly demonstrate this point. Their gestation period has slid to 22 months, almost 2 full years. Evolution is not driven by the survival of the fittest. The species that survive seek a balance with their fellow species and exist within those limits. All others become extinct. The fundamental stability within evolution leads to the principle of inevitable discovery. The body is of finite complexity with a finite number of possible birth defects. Eventually, each and every one will occur. The ones which are beneficial are incorporated into the design. The ones that are not are discarded. Even if a birth defect happens only once every million years, after 10 million years, the species will have had 10 chances to incorporate the beneficial defect into the design. Therefore, the process of evolution is not random. At this point, a slight diversion is required to describe the nature of predictability in random systems. Take a standard die. It has 6 sides labeled 1 through 6. Throw it, and the number side that comes up will be a random choice of the 6 options. Any one of them can arrive with an equal chance. However, if one throws that die 6 million times and plots the results, the graph will appear as this. Throw the die another 6 million times, and the plot will be the same. Is it possible that the same side will come up all 6 million times? Theoretically, yes. However, the possibility of that outcome is statistically insignificant. Even more impressive, if the die is thrown 12 billion times, the graph will still appear like this. Viewing each individual toss, the results will look like this. Over time, the results will look like this. The experiment is based on a series of random events, but the cumulative effects are always predictable. And, unlike string theory that seeks to establish a link between the randomness of quantum mechanics and the predictability of Newtonian physics, this basic truth has been learned without the need to create any parallel universes. So, a system that is based on short-term random events can become predictable when the results are averaged over time. Can evolution's random path through time be predicted? We shall see. Imagine the species that has waited 1 million years for a beneficial birth defect. Then a miracle happens. One of their number has the defect, but the animal is gay. If the species has behavioral patterns to force gay members to mate, the defect will be passed on. Otherwise, the species will have to wait another 1 million years for the next time the defect occurs. In humans, this behavioral pattern to ensure beneficial birth defects are not lost to homosexuality is known as homophobia. Animal species that have the homophobic response are more likely to incorporate beneficial birth defects into their genes and are, therefore, favored by the evolutionary process. In the same manner, if an animal has the defect, but its color makes it unlikely it will survive, the beneficial defect will most likely be lost in the belly of a predator. Species that can reduce diversity are more likely to incorporate beneficial defects into their population. The best way to remove diversity is to eliminate any randomness in the survival of the individual animals. A lot of diversity can be removed if the randomness in the survival of the young is removed. Animals are hindered in 2 ways when they are young. One is that they are small and less capable of protecting themselves. In reptile species, where many offspring emerge at the same time, the survival of any given animal is more a factor on how full the predators are rather than their eventual capabilities. This effect can be seen on the population distribution curve. The predators will consume large numbers of the offspring across the entire capability spectrum without applying any form of natural selection. If a species waited 1 million years for a birth defect, it very likely will end up in the belly of a predator. The other factor is that the young do not know what animals to fear. Watching predators eat their siblings will help to show what animals are to be feared, but some of their numbers must always die first. Once again, it is very likely the beneficial defect will end up in the belly of a predator. Both of these problems can be solved if the mother stays with the offspring. She will protect them from predators and guide the development of the pattern response table by showing how they must act. Now the survival of the offspring is related to the capabilities of the mother, and these attributes have been passed along to the young. Fewer of the offspring will end up in the bellies of predators. This will improve the chance that a beneficial defect will be incorporated.